I love my pencil. It's such a beautiful pencil. I've made such beautiful drawings with it. Take a look at what I've done. Look at this drawing, or this drawing, or even this one. In fact, this drawing is going to be the focus of today's video. The sad part of today's video, though, is as much as I love my pencil and the beautiful things it can create, I've recently discovered that doing or creating schematics on a computer, on a PC, and using them to create a PCB, a printed circuit board, is a lot easier than repeatedly trying to draw things with a pencil. So today we're going to get back into the second part of our PCB design series. And by the way, we're like 19 episodes into our creation, where we've gone from scratch to creating, well, nearly creating a printed circuit board for a custom made LED driver that allow us to change the intensity of some high powered LEDs. So it's really cool stuff. And if you haven't seen the previous videos, make sure you look at the journey and watch some of the previous videos. I'll make sure to put a link in the description down below. But for now, let's get started on the second part of our PCB design video. Okay, so in our first part of the PCB design video, we started to take this monstrosity and turn it into something that looks like this. Here's the block diagram we created on the last video. Okay, I have to admit, this wasn't exactly the same block diagram we had in the last video. The previous one looked a little bit more like this. Ooh, I don't know what I was thinking. Every single video up until now, I used a nice ruler to make my drawings, and this one, I fell apart. So I could no longer look at this, and so I created this. On the first part of the PCB design video, we took this portion of our circuit, the indicator portion, and we started taking the schematic that we designed and turning it into a printed circuit board. This was the schematic that we started with. And then we took this schematic and we turned it into the printed circuit board that looks like this. Now, this isn't the entire completed circuit board, as you can tell. There's a whole lot missing. We just got started. And today, we're going to focus on the logic part of this block diagram. And we're going to take the schematic of that logic and add it to the printed circuit board that we have so far worked on. And this is the beautiful schematic that we're going to work on transforming into that printed circuit board today. So when I started working on transforming this schematic into the PCB, I ran into a challenge. And I'm going to have to dig into the schematic for us to understand where that challenge was. Okay, so looking at the schematic, if you recall from one of the previous videos where we built this up, and if you're interested, I'll put the link in the description as to the specific video where we actually designed the schematic. But if you recall from that, what we did is we created some of the logic pieces. So these are two 4012 logic gates. These are actually NAND gates, 4-input NAND gates. And down here we have the 4516 binary counters. And these counters, as we know or recall, count up or down depending on the intensity level of that LED that we want. And these NAND gates will prevent the counters from going beyond the intensity or the maximum intensity that our drivers are capable of delivering. And on the left side of the schematic, we have the buttons. So here's the up button and there's the down button. Now, when we designed this schematic, what we needed at the time was a CMOS inverter. Again, go back to the previous or one of the older episodes that I'll link if you want to understand exactly why we needed a CMOS inverter, but the fact is we needed one. And it just so happened that when I was doing this schematic, I noticed that half of this chip, the 4012 chip, was unused. This is a 4-input NAND gate. So I was like, this is super convenient. Let's use this as our CMOS inverter. And so that's exactly what we did. You can actually see one of the leads coming up from this up switch, and it goes into the D input over here of the 4012. And the other three inputs are tied to high. What that means is whenever this up switch or that lead on D goes high, then the output, this J, goes low. And if the input on D is low, then the output J will go high. So this worked as a CMOS inverter. And for the purposes at the time, it was perfect. But the problem is when we started to design our system modularly. Let's take a look at the block diagram and we'll figure out what's going on here. When we designed the block diagram, we did this really deliberately. We did it so that we can choose to either use buttons to increase or decrease the intensity of the LED, or use a rotary dial to increase or decrease the LED. We've already built the circuits for these, and the appropriate videos are going to be in the description below. But we also did it so that we can swap it out, right? Maybe we want to create a total circuit that uses the buttons, and other times we want to create a circuit that uses the rotary. But regardless, the logic is always going to be there. So the logic couldn't change. It needed to stay constant, and it needed a few inputs that are coming in from the buttons. But the way we designed our circuit didn't work like that. The way we designed our circuit mixed that bit up. We actually had a lead coming in from the buttons to the logic and then back out again. So we needed to change that. And this is where I started to see the usefulness of my pencil begin to deteriorate. So I put my pencil to work, and I started drawing the new schematic that considers what we just talked about to make sure that the buttons could be isolated from the logic. And as I started drawing this, I started making the few mistakes as you normally would. I had an eraser, of course, so I started erasing, and I kept thinking to myself, there's got to be an easier way. And as we've discovered in the first part of the PCB design video, we're using software to create our PCB. You could also use the same software to create schematics. And the advantage, or one of the advantages of doing it in the same software, is that you can synchronize the two together. So I said, okay, let me give it a try. So the first thing that I did is I took the original circuit from the indicator portion. I said, let me convert this to a schematic. And I did. It looks like this. There's the schematic of the indicator portion of our circuit. Now, this schematic is basically the same as the drawing. And I can do this really cool thing within this particular software is I can actually highlight the individual nets and watch them blink on my screen so I know where they're connected. So if I want to look at the net for data 0, I could click on it on the list over here and see all of the different pins of the ICs or chips that need to be connected together. And I can do the same for data 1 and data 2 and data 3. And suddenly it makes following along a lot easier. So once I finished with the indicator schematic, I then transitioned to this. And I said, okay, I'm going to take this and I'm going to transform it into a digital schematic. But I need to do it deliberately. I need to do it properly. I need to take the logic part of this and put it in its own schematic, and take the buttons and put it in its own schematic. So let me show you what the logic part of this is. I'm going to bring that up on the screen now. So on the screen, on the digital schematic, you can clearly see the 4 chips that were on the original hand-drawn schematic. Here are the 4012 NAND gates. There's 2 of them. And here is the 4516 counters, the binary counters. There's 2 of them. All the other stuff is missing, but there's a few other peculiarities here. Well, not peculiar. There's one peculiarity, but there's a couple other things you notice. Is first of all, my plus 12 and ground are down here. These ones are the inputs to the logic, and that's the same inputs that you saw in my schematic, the reset, direction, ground, and press. I'm going to get into them a little bit more detail somewhat later, but we can also see the outputs from this logic, and we can see data 0 all the way to data 5. Here's the peculiarity that was not in the original schematic. We'll get to what these little triangles are in a little bit, but first I want to show you the other half of that schematic drawing, the buttons. And this is the result of the schematic drawing for the button side. So the left half of my circuit drawing. It looks mostly the same, but I had to add a few things into here. So here are the outputs from the buttons: clock, reset, press, direction, the 4 outputs that I need to go into my logic. And here is the up button. Here's the down button. And I also have a reset button. I threw this in actually kind of at the last minute, because although we didn't have it in the original schematic, if you remember from the video, I had actually put the reset button into the breadboard when we built it, and it worked. And it was kind of a thing I just did on the fly, but it worked out to be quite useful. So I wanted to make sure the reset button was still in there. So I've drawn it into the schematic as we have here. And then what I did is I said, well, that CMOS inverter that we were using in the 4012 chip, I said I needed to replace that. So, okay, I'm also going to go back to another video where we did. I think this was video, which video was it? Maybe episode 13? I think it was episode 13. It was quite some time ago, where we were actually designing the up-down button. And when we were designing it, we realized we needed a clock. We needed to generate a clock signal that would just go up and down, up and down. And at the time, A chip that I had lying around on my workbench was the 4007 chip. And it's such a versatile chip. This thing is basically a bunch of balanced NMOS and PMOS MOSFETs. So it's a really versatile chip. But what I did with the chip is I essentially configured that 4007 chip to behave like three CMOS inverters. That's all we did. And then we took those CMOS inverters and plugged them in a certain way so that we can get a little bit of a clock pulse. And if you're interested in how to do that, make sure you go watch episode 13, I think it was. Anyways, so now here we are today where I need a yet another CMOS inverter, but that 4007 chip was totally used up in order to generate those three CMOS inverters. Well, it turns out there is another chip out there in the market that has six CMOS inverters in it, and it happens to be this one, the 4049. I also happen to have one. So I said, let's use this. So I put the 4049 chip in, and that means that I still have the three inverters that I had last time, but now I have actually three extra ones. So I used a fourth inverter, and now with this chip, I still have two empty slots on this chip that remain unused. So now we have taken our original schematic and split it up into a logic schematic and a button schematic and arrange them in such a way that it'll abide by our new block diagram. So now I can have a logic center and buttons which I can replace with a rotary if I needed to. So now that the design is complete, we can take our new circuits and start putting that into the printed circuit board. Let's do that. So here's the logic schematic that we're going to transform into an actual circuit board. So let's take a look at the circuit board as it is today, or the printed circuit board as it is today. There it is. This is the printed circuit board, which includes the indicator component only. And we're going to start adding all of the chips to put the logic center in here as well. Let's start with the four chips. There they are. So we have the 4012. This is the lower significant byte of the counter, and here is the upper significant byte of the counter, 4516 chips. And you can see I've already ran some traces together to make sure that it's all connected. And oh, look, here's one of the advantages of having a schematic in the same software that you're building the PCB. When you have a schematic like this, I can see, look, this track over here, or this trace over here that happens to be data 0. So I can highlight data 0 in my PCB and see how the data 0 lines blink. Notice there is a data 0 on the indicator side, which we have not yet connected. We're going to connect them up later. But for now, you can clearly see where all the data 0 nets are. And you can also clearly see which chips they connect to and where. And if I go back to my schematic, I can do the same thing here and click on data 0 and make sure and confirm that it is the right chips and the right locations where those things are being connected. Beautiful. Trying to do this with a pencil and highlighter? Oh, man. So now that we got the four chips in, let's start adding a few more components. The next thing I want to add into our PCB is the reset, not all of the circuitry, but just the reset components. So we're not going to put the switch in. The reset components are these things. This is a capacitor over here, and this one here is a resistor. So let's put those in to our PCB. And I'm going to fit them in right over here. It's going to be hard to see. Let's zoom in a little bit so you can actually see them. There they are. So here's our resistor and there's our capacitor. Also, you may have noticed I kind of skipped over it. We actually have a few more places for capacitors over here. And those capacitors are the bypass capacitors. So there's a capacitor over here that we're going to use as a bypass for the 4516, the upper or the most significant bit. This bypass capacitor is for the lower significant bit, and these two bypass capacitors are going to be for the 4012 chips, both of them. So there's our reset component. Let's add a bit more. I think the next thing I want to put in is I'm going to put in these components over here. So both of these NAND chips have a diode going this way connected to a resistor. And the function of these two diodes connected to that resistor is so that we can take both of these outputs of the NAND gates and combine that together. Essentially, we're taking two 4-input NAND gates and combining it so that now it's a single 8-input NAND gate. And if you go back to the original design circuit, you'll see why we needed that. I'm going to pop them in right over here. Let's zoom in a bit. You can see them. There they are. Here's our two diodes, and here is the resistor that we've put in, and we've wired it up accordingly. Let's keep adding. So the next thing I'm going to add is these peculiar little triangles. What the heck are they? Basically what they are is, well, I know I have data 0, which is here, data 1, data 2, data 3. So that's the minimum 4 bits. So at the very least, we're going to have 16 shades of intensity. 4 bits gives us 16 shades. Now, as an option, I might want to enable the 4th bit, which would give us 32 shades. So data 4, which comes out of the counter over here. But remember, the reason I need to make sure it impacts our logic is because if we're using 16 shades, I need the counters to stop when it gets to the maximum intensity, 16. But if I'm using 32, I don't want the counters to stop at 16. I want them to stop at 32. So I need to change my logic a little bit. And so this data 4 line that comes out of the counter, it does go to the output, but it also gets fed into one of these counters as an input, but it's an option. And that's what this triangle is. So this triangle is serving as basically an optional jumper. Either I'm going to choose input A, in this case is data 4, or I'm going to choose input B. In this case, it's just a positive 12. So that's all this is. It's basically a jumper. I have 2 of them because I need another one, right? I need another one to say, well, maybe I want it to go to 64. And embedding them onto the PCB turned out to be very simple because in a physical world, all these jumpers are, it's just a piece of wire. So I need some mechanism so that I can either connect position A to the common or position B to the common, but not both. And I need that twice. And so I did that in the PCB. Take a look at this. Here they are on the bottom left side. I'm going to zoom in so you can see them. All right, so here are my 2 jumpers. So these are the 2 jumpers over here, and you can see what there's a trace going into the bottom of both of them. And that one is data 5, and this one is data 4. So I can actually use my cool little technique here to highlight data 4 and data 5. So you see them going to the jumpers. So this is one end of the jumper. In the middle is the common, and you can actually see a little bit of a yellow line. This yellow line means that they're not actually connected by a trace right now, so it's a missing trace. But I have added them to the net, so these 2 have to go to the appropriate pins on the 4012. The top pins of these jumpers are going to be connected to the plus 12. You can actually see it already when I hover over it. You can see it's already been connected to the plus 12, but I don't actually have a trace. I'm going to add the trace shortly, but that is how these things are supposed to be connected. Now, to help whoever puts this together understand what they mean, I've printed some things right onto the board. And so let me hide some of the top copper, and you can actually see what I've printed. So here are my 2 jumpers, B4 and B5, standing for bit 4 and bit 5. And then there's an enable and disable. So the bottom piece here means that the enable means that the bottom 2 pins need to be shorted or connected with a piece of wire. If you disable bit 4, then the top 2 pins need to be connected with the wire. That's how I wanted to implement the jumpers. You can see it's actually pretty straightforward and easy to be able to implement some flexibility into the printed circuit board design. So the next thing I did is I wired up the other or the common pins within those jumpers. And these are the 2 common pins that I put in, and I labeled them in the net as a data 4 optional. So you can see it's highlighted over there, and data 5 optional highlighted over here. These are the common pins going to the appropriate pins on the 4012 logic gates. So those are connected. The next thing I'm going to do is wire up all the power to all of these chips. And there it is. So I brought plus 12 volts in from the top down into the first 4012 chip over here, and you can see how it's also connected to the bypass capacitor. It continues on to the next bypass capacitor and also connects to the 4012 chip over here, and then it kind of goes around here, connects to this bypass capacitor, and it stops. I've connected these 2, 4516, the plus 12 over here together, but notice they're kind of isolated and not connected. I've also connected these 2 together. These are the plus 12 pins of the jumpers together, so they're now plus 12. But they're isolated. Also notice that all of the main power lines that go to the chips and the bypass capacitors, I made them fat. And if you remember from the first video of the PCB design, I want my power traces to be fat because, well, the chips need power to run, and I don't want to restrict them in any way. The jumpers are different. They don't actually need any power to run. It's just a signal. So that's why I left this one at a regular thin trace. But the next thing I need to do is I need to connect them because they're on islands right now. And so in order to connect this pin to this pin or make these nets connected, I need to go down to the second layer because I can't cross any green lines if you remember from the first PCB design video. So let's make the missing connections. And here you go. So you can see there's the layer 2 line, the layer 2 plus voltage line, the blue one that goes underneath these green, and it makes that connection over here. It also makes a connection over here to help connect our reset pins as well. And finally, there's the thin blue line that goes in underneath to connect the plus 12 from our jumpers. So if I zoom out a little bit and highlight my net for the plus 12 volts, you clearly see that they're all connected. Well, let me zoom out a little bit more. There you go. Clearly see that they're all connected. So all I need to do now is add my ground. And there it is. All of my grounds all squigglied out and made sure that they're connected to everything. So if I highlight the net, you'll see how the ground is now fully connected. So right now, what we've done is we've taken our logic center, this bit right here, and added it to the PCB, which already contains the indicator. So far, we're not nearly done. We still have quite a bit more to go. We still need to add the buttons, the rotary, and we need to work on the driver. And we also need to make sure that this thing is connected. But look, our PCB has got quite a lot of space on here to be able to fill in the rest of the components. I'll see you next time when we actually start working on the buttons, and perhaps even we'll get the rotary in there too.